I will actually speak about a stack of 3 open source projects. And if the uppermost layer is the Piraeus Datastore project, which does all the interfacing between Kubernetes and these lower levels of the stack. And below that is LINSTOR. That's like an orchestrator for DRBD volumes and for logic volumes, either managed by LVM or even CFS. And the lowest level component of the stack is called DRBD. And that is a Linux kernel driver to replicate block devices. And yeah, the agenda of the talk is I will first go into Piraeus, and then LINSTOR and DRBD, that will be like a little bit mixed. So let's start with the operator. So what is it doing? It deploys this all the components of the software-defined storage to your Kubernetes cluster. And that consists of the LINSTOR controller, the LINSTOR satellites, the kernel module, and here we have variations depending on your Kubernetes distribution, where the necessary kernel modules are coming from. Then nowadays, LINSTOR stores all its metadata. The metadata is which volumes do exist, which storage classes do we have, what storage nodes are in the cluster. These days, that's all in CRDs, custom resource definitions. In the past, we had it in etcd, but fortunately, we moved on from that. You need some physical storage devices, since this is all about software-defined storage. The storage devices might be in the nodes that also host your containers, so sometimes referred as HCI, hyper-converged infrastructure. You also can have disaggregated storage servers. Yes, it comes with a CSI driver. Also, this is deployed by the operator, snapshot controller, topology awareness, etc. The CSI driver itself has the usual capabilities you would expect from a CSI driver. CSI, that's the container storage interface. I guess I don't need to lose any words on that. And I would say its capabilities are pretty standard, so provisioning, attaching, snapshotting, resizing existing volumes online, of course. The most volumes will be read-write once. We also support read-only many, and for read-write many, we need an NFS operator. So this is a different kind of beast. For all the containers, it runs in file I/O mode, so by default XFS. But if you prefer, you can also use ext4. Block I/O mode for KubeVirt VMs. And for the KubeVirt VMs, it also supports live migration, I think, an important aspect. And built into LINSTOR is also the capability to ship complete images and snapshot differences into S3 object storage or to another site that also has an instance of the SDS running. Very often I get the question, how is this different from Ceph with Rook operator? Or how is this different from, you name it, the other ones? And the answer, very short answer is we use very little resources. And this starts at the number of containers the SDS will create in your Kubernetes cluster. And so we will have 3 containers per kubelet node, plus 3 for the cluster. That's it. And the last time I looked, it was significantly less than compared to the other projects out there. The other two items, I will go into that when I discuss the low-level parts of the stack. Yes, this is all open source, so you find it on GitHub, Slack channel, and so on. And by now it is a CNCF sandbox project. Now, let me switch to the two lower parts of the stack. So the first aspect is we want to keep your data forever, and NVMe drives or nodes might fail, so we need to replicate that. The part we do the replication with, it's called DRBD, and that's a driver within the Linux kernel. So here on the orange box, that is like the Linux kernel on one of your physical machines, and you have this I/O stack on the left side, from the file system all the way down to the physical storage device. And at a certain point in the stack, the DRBD module is inserted, and it replicates all the write requests coming down the stack over to the other node, and acknowledgement travels back, and only if the local write completion comes up and the remote acknowledgement is there, then it signals I/O completion to the upper layers of the stack. That is synchronous replication that you would use within a data center. It can also be configured to be asynchronous. This is what you would use on the long distance between data centers, between East and West Coast, whatever. So in the previous illustration, I had two servers, two sides of the story. And it exposes a virtual block device on Linux level, and then the CSI driver mounts the file system on top of it and hands it over to Kubernetes. And this is how it gets into your container. In the moment this virtual block device is opened, it promotes its role to primary, and with having one node in primary role, that determines the direction of replication. So moving a container around is pretty transparent, because when a container is stopped, the file system gets unmounted, it changes its role to secondary, and then you can promote it somewhere else. And the promotion will happen implicitly by the stack being built on top of it. Then DRBD itself can also replicate physical storage devices of different properties. Let's say you have a very fast NVMe storage, and on the other hand, RAID 5 of rotating media. And it can replicate such setups with multiple storage devices in a consistent way. And an example for that would be a database that wants to have it write ahead logs on the fast storage and the table spaces on the slow storage. But these days, we put everything in NVMe drives and don't care about details like that. DRBD is these days no longer a two-node technology. It can mirror to multiple nodes concurrently. So here in this illustration, we have like a 3-node DRBD cluster with 3-node replication. Now, when we take a step back and how does this fit into our Kubernetes model? So each of your persistent volumes on the Kubernetes layer will become one DRBD resource and one DRBD cluster by itself. Here on the slide, you can read that every DRBD cluster by itself can consist of up to 32 nodes. That means that's the numbers of replicas of a single persistent volume. That is not the limit of nodes in your cluster. So we have customers running hundreds of nodes in a Kubernetes cluster, and each of the persistent volumes becomes either a 2-node or 3-node DRBD cluster, and LINSTOR places this among your nodes. And either two or three replicas is that what most people do. if you have setups with data centers in different cities where you want to protect against disasters, then more replicas might make sense, but I have never ever seen somebody doing 32 replicas of his block data. An important ability of it is the management of diskless nodes. So one of the advantages of having 3 nodes and one without replica is that the LINSTOR DRBD combo can enable quorum. And quorum is a very important algorithm to protect yourself from split brain situations. And this way, split brain never happens, and you only have 2 replicas, so you keep your hardware investment down. And the other important property, you can move this primary node around. So LINSTOR changes the DRBD config on the fly if the volume needs to become accessible on another node, right? And yeah, also another way a node might become a diskless node is if the physical storage device in the node breaks, right? Then it becomes a diskless node transparently, and it shields the stack above the application from any I/O errors. So if there was a read request, a write request to the local block device while it fails, okay, it removes that backing device and reissues the I/O operation to one of the nodes. And maybe last not least was what I should mention here. It also does efficient resynchronization. So just imagine in your big Kubernetes cluster, one of the physical nodes is down, not a big deal, right? The workload is moved to other nodes. But these replication sets have one replica that's not online for a certain amount of time. So when it comes back, it needs to be resynchronized, so all the updates that happen in the meantime, right? And this resynchronization can become expensive, and so we have a change tracking bitmap that we only resync what was changed in the meantime while it is away. Yeah, I think that's it. Now, keep your services online. So this storage stack is also available for a few other orchestration technologies outside of Kubernetes. But today, let's keep the focus on Kubernetes, right? Let's go into LINSTOR. So LINSTOR is the open source project and the software that gets deployed by the Piraeus operator. And you have one controller running, one controller per cluster. You have a satellite running. The satellite is completely stateless, configurationless. It runs on all the nodes taking part in it, so all the compute nodes where you have containers running, all the storage nodes, or the combined nodes, right? The controller runs in one instance, but it can fail over to other instances, to other physical machines if this one fails. Maybe what's important to mention here is that this control plane in this sense is LINSTOR itself, because it creates the logic volumes, it creates the DRBD configs. It's completely independent of the data path of the replication. So the LINSTOR controller can be restarted. It can be even upgraded while your workload does I/O on existing persistent volumes. Upgrading the data path can also be done independently of the controller, but it requires a different kind of procedure, of course. And yeah, and the structure is the LINSTOR controller has a REST interface, might be SSL encrypted, And from top of that, then the CSI driver uses the REST interface and also a few other drivers. And I think that's it for this slide. Now let's exploit by example. Now let's consider we have a cluster of 6 physical nodes, and each of those nodes has built-in storage devices. Now we get in a request via the CSI driver for a new persistent volume, and let's say it's the orange one, right? Then LINSTOR knows, okay, this VM or this container is going to start on the top left machine. So it tries to place one of the replicas on exactly that machine. And the storage class in this example wants to have 2 replicas. So it searches for another node to host the second replica of the data set. Notice the advantage of co-locating one replica with the workload. That means we get read requests without creating traffic on the network. And as the cluster scales, it's always the network traffic that becomes a limiting factor. So read requests, let's say, for free, virtually no overhead. And for the write requests, okay, we create network traffic and additional latency, what we need for transferring the data over the network. And also the black workload is also in its optimal position. But in case it's a KubeVirt VM, we might live migrate it. In case it's a container, we can also move it. Then what happens transparently in the background is that this DRBD configuration is changed. It gets a diskless node added, so the KVM process or the container can access it now on another machine, but the data is still where it was, right? And for read requests, it does load balancing in this kind of scenario. So you get nearly double the read performance of the individual NVMe drive you have here in the back end. Granted that you have a 100 gigabit network, right? Yeah, and then there is a few policies in LINSTOR that would allow you that the system tries to migrate the storage to the workload after a certain time parameter. So let's say you have it in the diskless configuration for 60 minutes. You want that it tries to move the storage where the workload runs. Of course, at first it checks if in this volume group is enough space available. It would create a logic volume there, start the DRBD resync, and when the DRBD resync is done, it will automatically remove the third replica because the policy of this storage class only wants 2 replicas. So this is a feature you can enable. You don't need to enable it. I think it's not enabled by default. By default is the cluster shouldn't do anything you don't expect. So that's our philosophy when it comes to defaults. What type of applications do our customers run very often of that? We see most customers running I/O demanding workloads, like databases, online transaction processing, or analytic databases, message queuing systems, probably also AI workloads. We are just in the position, we do this infrastructure component. Our customers not really tell us what they run on top of it. They just talk about the issues with us. Here, the fourth value here. Let me tell you a few words about the organization behind this. So as I already mentioned, it's all open source. So all the stack, everything you saw so far, from the Piraeus operator to LINSTOR to DRBD itself, all is open source components. The source code is on GitHub. We are the main driving force behind it. we're a small company, about 40 people, most of us in Europe, 15 of us located in the United States. And we have a business model that's, let's say, comparable with the business model of Red Hat. We sell support subscriptions to the open source software. We make it very easy, accessible as part of the open source subscriptions. So pre-built containers with pre-built kernel modules, etc. Number of customers, and yes, what I'm talking here about is the Piraeus Datastore project is then, when it comes to the Limbit product names, it's called Limbit SDS for Kubernetes there. And let me give you a few hints about performance. But performance is a difficult topic because it changes every year with the hardware you put there, right? So and with that also the bottlenecks in the software are a moving target. Let's put it that way. So first of all, we are really optimized to deliver I/O performance. So IOPS and write latency. This is what not keeps me awake at night, but makes me go to work every day. So it is about optimizing our software within the kernel, minimizing number of context switches and all those gory details. Most of our customers replicate over TCP/IP Ethernet networks, but we also have a dedicated driver in the end for RDMA networks. If you want to achieve the highest possible performance, RDMA is your route to go. Currently we see here for replicated writes 3.5 gigabytes a second in throughput. But as I said, might be different next week. The other aspect is we decide where the replicas go in the moment the persistent volume is created. So at runtime, at I/O time, all that is set. We're built on top of existing components. So DRBD itself, it is around since 25 years. On top of LVM or CFS for the local volume management, Lux and VDO, depending on what you want to have in your I/O stack. What's the difference between LVM and CFS? I basically tell people, go what you have in your underlying Linux distribution, but there are certain limitations where, let's say, LVM works until up to 1,000 logic volumes on a machine, but is bad in scaling to more than 1,000 volumes per physical machines. CFS has better scalability, but its performance is not as great as the performance of LVM in the first place. So a few options that you need to decide before rolling out this project. And last not least, it is really very well suited to be used in a hyper-converged way. Why that? Because the CPU consumption and the memory consumption of all the components is low, and it is very predictable. So in the moment you know how many terabytes of SSDs are in your servers, you can calculate exactly how many gigabytes of main memory DRBD might use in the worst case. And it's, for today's servers, it's really like nothing. And you don't see any surprises later on. And yes, so here are a few benchmark results from the recent years. So still have in this 2019 numbers. The reason why I still have them in here is at that time Intel had they called it Builders Lab, and they rented it out to different vendors of software-defined storage products. And look for the results. We had the best result on this specific 12-node cluster. And then last year, we got our hands on this 3-node ARM machines. And I mean, you see more IOPS with less nodes. So this is why I'm saying it changes every year. So I linked the papers and results and all that. And that is basically my presentation. I hope you have some questions to fill the last 5 minutes.
Thank you very much for this session. We do have quite a lot of questions. So let's get them one by one. Does the solution modify spot placement? What's your take on this?
No, not at the moment. It doesn't do that.
Okay. All right. It's moving fast. How is storage accessed when no local replica is available? Let's take this one.
Yes. So then on the node where no local replica is available, the DRBD driver is also loaded, and it exposes a virtual block device, and it talks the DRBD protocol to the nodes that have a backing device. So you can think of it, it is on a very high abstraction layer. It is similar to iSCSI, right? iSCSI initiator to iSCSI target. Just with the difference, it can talk to multiple targets concurrently. So it can do load balancing in reads to achieve higher bandwidth.
Very cool. Let's see. Is data always going to be collocated with application workloads, or could you build a dedicated storage cluster?
Yeah. So it's not always collocated. Collocation is like an optimization. It does if possible. But nothing holds you from having a dedicated set of compute nodes and a dedicated set of storage nodes. Just make sure that you have a reasonable network.
Yeah, network is always the case here. How does it compare to Longhorn or Rook?
Yes. So Longhorn is, to my knowledge, let's say, purpose-built for Kubernetes. It depends on Kubernetes abilities. This is a little bit different. It was around long before Kubernetes existed, and this is an adapter to an existing software stack. So in that sense, we are independent of Kubernetes. It's also available for other orchestrators. And what's more relevant for you is it will give you more I/O performance for less CPU investment and less DRAM investment. And it will require less number of containers in your Kubernetes cluster. And about the same is also true for ROOK-Ceph.
A lot of advantages then. Is there support for on-disk encryption, or encryption is off in-flight traffic?
Yes. So for encryption, we offer, for encryption at rest, we offer that we manage the LUKS stack for you, so LUKS and deencrypt. And then LINSTOR manages all the keys for that. In case you have multiple tenants on it, you have different set of keys for each tenant, etc., etc. It can also place the data on SED drives, so that's self-encrypting SSDs, and manage the keys for the SED drives. With the SED drives, you have the advantage that you have the encryption off the main CPU. It happens in the drive. The disadvantage is you cannot have different keys for different tenants, right? So we do both. And of course, it costs a little bit of performance. We can also do encryption of the network traffic, of the replication traffic. So for that, we do TLS out of kernel space, and it costs, you get 30% of unencrypted.
Regarding performance, actually, we have a question. Regarding the performance figures, 25 milliamps, how much is caching involved?
There is no caching, like in the sense what Ceph is doing. So it always goes to the physical underlying block devices, except for the caching, let's say the Linux file system layer does with the page cache and the small buffer cache. But you can ignore the buffer cache these days. The page cache is the only cache.
I think you already answered the question, but is there an ARM64 build for Piraeus? Can it run on a cluster or Raspberry Pi? You briefly had...
Yeah. Regarding ARM64, I think it's available. So the ARM64 builds, they are ready-built containers for ARM64.
And I think the last question so far, is it good on network storage? Does it work like for SAS, SAN, or NAS?
You can use it on a SAN, but the question is, what is the point?
Yeah. I think it's more related like for home labs or something like that.
It's, I wouldn't be here and I wouldn't be a sponsor if all of our users were home lab users.
True.
So we have users, lots of our paying customers are users in the financial industry, pharma industry, and it's infrastructure software, so it's in all the segments.
Fair enough. Do we have one last question so far? If not, then we'll close this session. Philipp, again, thank you very much for this very interesting talk. A big round of applause, please, for Philipp.
Thank you.